So this is the second part of the video where I showed that when I move the bottle in this direction, the bubble moves in the direction of acceleration. Now, as per Newton's first law of motion or the law of inertia, the bubble should move in the opposite direction of acceleration. Now, in the first part of the explanation, we had understood the concept of inertial and non-inertial frame of reference and the mathematical framework behind them. Now, in this video, or the part 2 of the explanation, we will be applying the mathematical formula to understand the motion of the bubble. Let's start. So it is clear from the previous part that the frame of the bottle is a non-inertial frame of reference. So the formula in our use will be F equals to m into small a minus m into capital A. As you can remember from the mathematical formula of non-inertial frame of reference. Here this small a is the acceleration of the bubble according to the bottle, and this acceleration is due to the force applied by some external agent. Now in this case the external agent is me because I was applying the force, and here capital A is the acceleration of the bottle. Now let's deal with small a. I mean, what will be the value of small a here? Let's try to find it. Now for this, we need to note two important points. Number one, A is the relative acceleration of the bubble with respect to the bottle. This relative acceleration term is extremely important here. And the agent of this acceleration is me. That is clear from the video. Now see that I didn't apply the force on the bottle or the water or the bubble individually, but I actually applied the force on the whole system. It is clear from the video that I applied a force on the bottle, and inside the bottle there was the water and the bubble, so together they all moved. So I applied a force on the whole system, and the system contains of course the bottle, the water and the bubble. Now if due to my applied force on the system, the whole system moved with an acceleration, suppose a dash, then all those three, the bottle, the water and the bubble, that include or that consist the system, they all will move simultaneously with an acceleration of a dash. Similar to the case, suppose a train and you are inside this train. This train is moving with an acceleration of a dash. Now if I am standing outside, then I can't just say that only you are moving with an acceleration of a dash or only the train is moving with an acceleration of a dash. Rather the whole system, that is you and the train make up the system. So this whole system is moving with an acceleration of a dash. Similarly in this case, as the system contains all these three, the bottle, the water and the bubble, all these three moves with an acceleration of a dash simultaneously as the whole system is moving with an acceleration of a dash. Now let's consider a very simple example. Suppose this is your friend's car and this is your car. Now both of them are moving with the same velocity. Now tell me that will you see that your friend's car is moving with some velocity with respect to you? Of course, it is a very simple thing, or it is a common sense that you will see your friend's car to be at rest according to you. That means if two cars are moving with the same velocity, then the relative velocity between them should be 0, right? Similarly, in our case, as the bottle, the water and the bubble, all these three that constitute the system are moving with an acceleration of a dash, then from the previous example it is clear that the relative acceleration of any of them with respect to another will be 0 because they are moving with the same acceleration. Now let's come back to the first important point where I mentioned that this small a is the relative acceleration of the bubble with respect to the bottle, right? Now from here we had proved that the relative acceleration between each other or with respect to each other was 0. So the relative acceleration small a of the bubble with respect to the bottle, which was applied by some external agent, which was me, is 0. Now let's come to the formula, that is F equals to m into small a minus m into capital A. That is the force on the bubble according to the bottle, and the bottle is a non-inertial frame of reference. Now this small a becomes 0, so it is m into 0 minus m into capital A. So the ultimate formula that we get is F, that is the force on the bubble with respect to the bottle, our force on the bubble according to the bottle. As I mentioned, the bottle is a non-inertial frame of reference. The force becomes minus m into capital A. This capital A, as I mentioned before, is the acceleration of the bottle. Now you can call it A dash as we had considered before, but for now I am considering it capital A only. Now this is quite unexpected, because see, whatever may be the value of this m into capital A, for now forget it. For now we are concerned about this minus sign. This minus sign denotes that the force applied on the bubble according to the bottle is actually applied in the opposite direction of the acceleration of the bottle. And this was what said by Newton's first law of motion, or the law of inertia. But in the video we saw something else, right? That means, is there something wrong in this formula? Are we approaching in the wrong mathematical approach? See, actually the thing is that the formula is not wrong, but the formula is incomplete. Now I am giving you 10 seconds to think that what else should we have considered to complete this formula. So, if you have guessed that the water is playing some role here, then you're absolutely correct. Yes, the water is indeed playing some role here. But now the question is that, how is the water playing that role? Well, to understand the role of water, let's consider a very simple example. The example is that, suppose I have a jar of water. This is a jar of water. And this jar of water is placed somewhere where there is gravity or gravitational acceleration. Now, due to this gravitational acceleration, there will develop a pressure difference along the height of the liquid column. And everyone knows, everyone has learned this in middle school, that if I want to find the pressure at any point or at any level of water that is at a distance of h from the top, then it can be found out by the formula h into rho into g. Here h is the height of the liquid column, this height, rho is the density of water, and g here is a gravitational acceleration. Now let's consider a body that is submerged in this jar of water. Now again, everyone has learned this in middle school, that if a liquid has developed a pressure difference along its length or along its liquid column, then due to this pressure difference, there develops an upward force called the buoyant force. And this buoyant force acts on the body, which pushes the body up. Now, why am I mentioning it upward? Actually, see, the direction of this force is actually in the opposite direction of the gravitational acceleration. That's why I am telling it upward. In more general sense, I can tell this buoyant force is actually pushing the body against the force of gravity. And this buoyant force can be measured by the formula V rho into G. V is the volume of the body or the volume of the water displaced. Rho is again the density of water, and g here is the gravitational acceleration. Now let's return to the case of our experiment. In the case of our experiment, instead of gravity in the previous case or the gravitational acceleration, we have this capital A, which is a pseudo acceleration that comes out from this formula, F equals to minus of m into capital A. This capital A is a pseudo acceleration on any object, maybe the bubble or the water, according to the frame of the bottle. Now, as I mentioned before, that whenever a liquid or water is under an acceleration, in this case this was gravitational acceleration, there develops a pressure difference across the length of the liquid. Now in this case the length was the height. Now in our case, as the acceleration is pointing towards this direction, then along this direction there will develop a pressure difference along the length of the liquid. And this pressure difference you can call as pseudo pressure difference. I mean, this is a pressure difference that has developed in the liquid according to the frame of the bottle. Now, what is the formula for measuring this pressure difference? Well, it is very simple. See, in our previous case, we could measure the pressure at any point if we know the height. Then the formula was h into rho into g, right? In this case too, suppose at a distance x, if I want to find the pressure in this level, now why am I measuring from here? Why not from here? Actually, see, if I want to measure or know the starting point, I just have to go in the opposite direction of acceleration. In this case, this was gravity, so I had to go up. Now in this case, our pseudo acceleration is pointing towards right, so I have to go left. So this is a starting point. So from this starting point, if I go at some distance x, and at this distance x, if I want to measure the pressure difference, then it will be simple, x into rho into a. Now why x into rho into a? First of all, this x is similar to this h, just the distance. Rho is simply the density of water. And why a? Why not g? Because see, in this case our acceleration was gravitational acceleration, so we had to write g. But in this case our acceleration is a pseudo acceleration capital A, right? So I have to write capital A. That means the pressure at any distance x from the starting point will be x into rho into capital A. Now similar to the first case, that due to the pressure difference, there developed an upward force called the buoyant force. And why upward? Because it was in the opposite direction of the gravitational acceleration. Similar to our case, due to the pseudo pressure difference, there develops a pseudo buoyant force on this bubble that actually pushes this bubble forward. I mean, in the direction of the acceleration of the bottle. Now, why is it in this direction? Why is it not up? Because see, as I mentioned, these buoyant forces actually push objects in the opposite direction of the acceleration so concerned with the liquid. In this case, this was gravitational acceleration, so the buoyant force pushed the body up, that was in the opposite direction of gravity. Similarly, in this case, as we have the acceleration in this direction, the pseudo buoyant force will actually push this bubble in the opposite direction of this acceleration. That means it will push in this direction, and this direction is actually in the direction of the acceleration of the bottle itself. Now the thing is that how can I measure this pseudo buoyant force? Well, let's go back to our first case where the formula was what? V rho into g, right? So similar to this, in this case also the formula will be V rho into capital A. Now why is it V rho into capital A? Why is it A? Why is it not G? I think you know the reason. That is, in this case it was gravitational acceleration, so it was G, and in this case it is our pseudo acceleration capital A, so it is A. V rho into capital A. Now this is a very general observation. That is, Suppose I have a bubble of air that is submerged in a jar of water. mg is the weight of the air bubble and v rho g is the buoyant force on the air bubble applied by the water. Now it has been generally observed, or a very general observation, that is v rho g, that is a buoyant force on the air bubble, is always greater than the weight of the bubble. Why? Because the density of water is greater than the density of air. Now this is a very simple mathematical common sense, that if v rho g is greater than m into g, then obviously v rho capital A will be greater than m into A, because in this case also the water has a greater density than air, and v rho and m is same in both the cases. So the same term g and g doesn't matter in both sides, right? And also this capital and capital A doesn't matter in both the sides. Ultimately, the pseudo buoyant force is winning over the pseudo force that is applied on the bubble due to this acceleration. Now let's come back to the main formula, that was F equals to minus of m into capital A. Now after the reconsideration, that we have considered that the water is playing some role, after the reconsideration the new formula is F equals to minus of m into capital A plus v rho into capital A. Now why is it plus? Because it is in the direction of the acceleration of the bottle only, right? Now as we had proved that v rho into capital A is greater than m into capital A, that means the resultant of this value will be positive. That means yes, the force, I mean the net force on the bubble according to the bottle is indeed in the direction of the acceleration of the bottle itself, and that's why the bubble moves forward. Therefore we have proved.